Good morning, Annie.
Morning, Annie. Okay, so I think we could.
Can you hear us, Annie?
I heard something. Did you?
Yeah, I
Yeah.
heard everything.
Maybe her chat works.
Yeah.
Try chatting with us, Annie. Hmm.
How do we do the chat? Does that just show up down at the bottom?
Yeah,
It
it's
usually pops up like a bubble over her head, if I remember right.
Okay. Have you guys see anything?
nothing yet.
I don't see anything.
Oh, oh, right here. You see my chat that I just put in there?
Yeah, it just popped up on my screen.
Mm-hmm. Maybe your computer froze or something like that.
Yeah.
Possible. I think it's done it before, so.
Oh, now it's moving.
Mm-hmm.
Yes. All right.
All right. So does anyone have any questions on Lesson 6 preparation assignment?
So on the first part, I didn't really have any questions because it was pretty much straight from the book.
Yeah.
It was just all definition.
Yeah. Um, but yeah. So when it's asking about getting the sampling mean, where are you supposed to get like the different sampling numbers? I guess. Yes.
Oh, and in part B, the
Yeah. So like gives you all those numbers and it's the sampling mean. Is that just the one mean, or is it talking about different amounts of mean? Does that make sense?
yeah, with that little link program they gave you where it has the 3 graphs.
Yeah.
You can go through that, and it gives you a sampling mean for each set of random numbers you do.
Mm-hmm.
Oh, okay.
Yeah.
I see. So in like number
What's that?
on number 7. Let's see here. So is there 142,506 possible combinations of the 30 salaries drawn five at a time? So to find the sampling mean of this, you're supposed to use the generator, right?
Yeah, you can use the generator.
Do that.
And then I just kind of use for like number C. I mean, it looks like it's a normal graph, and it has a nice bell-shaped curve to it. So
Yeah, that's true. Okay.
let's see, how did I get to that? If I can remember here.
On number 7 or number 8?
Which one are you looking at, 7 or 8?
Oh, I was still looking at 7.
Okay, that's what I thought.
I'm trying to get into mine, but it won't click. Oh, there we go.
So Jeff, when you did that, did you plug it in or did you just do it all on calculator?
I didn't really plug in any of the real numbers. I just kind of went off this animated thing and did it 5 at a time. And
What do you mean the
of
animated?
course, I guess I probably didn't do it right.
What do you mean the animated thing though?
In the textbook, it gave you a link to, gave you an animated thing with 3 little graphs on it.
Oh really?
And I guess maybe I shouldn't have done it that way, but that's how I did it, and it worked out. I got the right answer. I guess it didn't give us answers to it, did it?
I don't think so.
So I'm just trying to look
Because it
at.
started giving us answers on number 8. They didn't give us any feedback for 7.
Yeah, I think just because it said the answers are going to vary so much.
Because I mean, depending on which ones you use, you could get a different mean for each of them.
Yeah. Oh, I see. So just randomly select 5 of the 30 salaries and compute them. Excuse me, and that's the salaries from part 1 of the preparation, right? Or no?
Yes.
In that like box and stuff.
Yeah.
That's what I thought it was.
Okay, cool. And we just choose that, get the mean of it.
Yeah.
Yeah.
Oh, I see. And then when it's talking about like with the larger amount of data that you have, the closer you're going to get with to the mean or whatever, or not the mean, but the sampling, I guess, whatever what it was trying to tell us.
Like the law of large numbers. Like
Yeah.
the more you take, the more it, or the closer it gets to the actual mean.
Yeah, exactly. Okay. So, how are we? Oh, never mind. I get it. That's pretty easy.
So if each of us selected 5, we should, if we all picked random numbers, we should get kind of different numbers, but they should be.
They should be similar.
Close.
Yeah.
Okay. Yeah, that makes sense.
All right. Any questions on number 8? So we have 8A.
So on this, to get that answer, you have to get the mean, or no. What is the little circle thing called again?
The standard deviation is the little O thing with the tail off the side.
And then the U is the mean, right?
Yep.
Yeah.
And then to get that answer, don't you do the mean? Is it the mean divided by the square root of standard deviation or backwards?
It is the. I kept having to look it up because I can never remember.
Yeah.
So So it's the standard deviation divided by the square root of the sample size.
Oh, okay.
But on 8A, you don't need to do that because it's just asking what the shape of the distribution of the sample means would be for this. And this one would be just a normal distribution because it's using a normal population.
How do you know if it's a normal population?
Because they use the simple random sample.
Oh, I see.
So it's just a normal
Yeah. Okay.
sample or whatever. I can't think of the word I want.
Yeah, I understand what you're saying.
Because the population is normally distributed. That's the next one. Since the population is normally distributed, you get a normal bell-shaped curve on it.
Yeah.
And then, so that's the answer to B. A and B are pretty much the same answer.
Yeah.
Because it just explains why it's normally distributed. Then C, your sample mean would be the same as the normal mean too, because it's just a sample of it.
Yeah. And then the standard deviation. This is what I was talking about, right?
Yes.
So the standard deviation of the sampling size.
So did I do that right? It's the.
Yeah, you did.
So this one would be 113 divided by the square root of 10, right?
Yeah.
Yeah.
Oops.
What'd everyone get?
That's what I did too.
My answer was 35.734.
Okay, hold on a second. So is standard deviation divided by the sample size? Is that how?
Square root of the sample size.
Square root of the sample size. Okay. Yeah. That's what I got.
Yep, I did too.
Awesome.
Yeah.
Hey, we can hear you, Annie.
Yeah, I thought I heard.
Oh, you can hear me?
Yeah.
Oh, there you go.
Oh, that's good.
All right, cool. I guess we could just start on the
Group assignment.
yeah.
Okay.
Alright, so number 3, when taking samples of n, when n equals 5, what is the shape of the distribution of means histogram when the parent population is right skewed? It would be skewed right still because it's only a population, they're only using 5 samples, right?
That's what I was thinking because it's such a small amount that it wouldn't be considered a normal.
Yeah.
Yeah. Right. Does that make sense?
Yep.
Okay.
And so that means the next one, number 4, would be normal because their population size is 100.
Yeah.
They have a large sample, so it'd be a normal distribution.
Mm-hmm.
That makes sense.
Yeah.
Number 5 would be normal as well because you're using a normally distributed parent population.
Mm-hmm.
Wait, so on 4, did we do that right?
Yeah, I was gonna ask. Maybe 4 is 4 skewed right as well.
I think 4 would be normal because it's using a large population size.
Mm-hmm.
When taking sample size, what is it? But it says that it's right skewed already.
Even if it's right skewed already, the central limit theorem, as the sample size increases, the distribution becomes more normal.
That's true.
Oh.
All right. Cool.
I'm pretty sure that's right. What?
Let's see. sounds right. I mean, what you explained sounds right.
Mm-hmm. Yeah, I guess that fall under that rule, so that makes sense, I guess. Are we on number 6?
Yeah, because even in this little thing, if you start off with this little animator that they gave us a link to, you can start off with it being right skewed, and even with a sample size of 25 gives you normally distributed. So
Okay.
So on that little computer that you're using, the random integer generator.
uh-huh.
So how are you doing that? I don't understand how. So you're generating 100 random numbers, right?
Yeah, so you can kind of put in the parent population is, whether it's right skewed. The options are normal, uniform, skewed, or you can do custom ones. So I just put it in skewed and put the sample size as 25 because that's the highest it'll let me go. And even when I'm generating it 100,000 times, it's giving me a normal distributed population.
Mm-hmm.
And that's with a sample size of only 25. So if it's 100, it would be
Be even more normal.
it'd be more normal because it's a larger sample size.
That makes sense.
Okay. All right.
All right, so number 6. So data drawn from a population that is normally distributed would give you normally distributed one. I don't know if all of ours are in the same order, but that's my first one.
Which one?
Data are drawn from a population that is normally distributed, and the sample size is small.
So that would be one?
It would be because the parent population is normally distributed.
Yeah.
Okay. And then number 2, that would be one too, wouldn't it? Because it's got the larger size, so wouldn't it?
And the population is normally distributed too, and that always makes it normally distributed.
Yeah. The third one wouldn't be, right? Because it's
No,
small
right
size.
skewed and small sample size would make it right skewed data. But the last one, data drawn from a right skewed population, and the sample size is large, because the sample size is large would make it normally distributed.
Yeah, that's what I was thinking.
So we have 3 of 4, right?
Yeah.
Yeah. Is Annie hearing all this?
Hope so.
Yeah, I hope so too.
Yeah. If she's not, we could probably do what we did last time and just
Email it to her.
email her what we got.
Yeah. Yeah, if she types us back, we'll just
Yeah.
say that. We can just email her and stuff.
Mhm.
All right. So number 7. Okay.
That's the theory of large numbers. On my list, I think it's the last one, but I'm not sure. If the sample size is large, the shape of sampling distribution will be sample mean x will be approximately normal.
Yeah.
And wouldn't it be the third one? Why wouldn't it be the third one?
That's what I'm trying to think. Is the third one central limit theorem, or is it the law of large numbers?
Yeah.
Oh, I think the third one might be. Oh wait, hold on.
I think it's the last one.
That's what I think too, Annie, because I think the third one is the law of large numbers.
Okay.
Yes.
Yeah, it is.
Okay.
All right, so number 8. So the mean would be 10 still, right?
Yeah.
Mm-hmm.
For number 8.
Yeah. Number 9, just 6.
I got 1.
Oh, okay.
I
Is
also
this
had one.
This is the one where you do the
Oh, yeah. Okay.
So,
standard deviation divided by the square root of your sample size. So it says 3 decimal places. Do you do 1.000 then?
so I got 1.897, and I must have done something weird.
Or I did something weird too, because it says 3 decimal places and I didn't get any decimal places.
I just got one.
You guys do. Let's see here.
Because I'm getting the square root of 36 is 6, so 6 divided by 6 is 1.
That's what I got too.
Yeah, I agree.
You got the square root divided by what? I'm sorry? Did you do
So,
6?
so the square root of 36 is 6, so 6 divided by 6 would be 1.
Yeah, okay. So, I was doing different.
But I don't know if I'm doing it right, though, either.
Well, I think I just did it wrong. Because I was using 2 different numbers. So I was using the mean. Wait, what was I doing? I forgot what I was doing. Yeah, so I did standard deviation divided by the square root of the mean. So that's wrong. You use the sampling size.
Yeah, because here's the formula. I just found it in the textbook. It's the standard deviation divided by the square root of n, which is n's your sample size.
Yeah.
Okay. Divided by the square root of n. All right, so. Oops.
So, but it says that we're supposed to round it to 3 decimal places. If it's just a 1, do we put 1.000 or?
Probably, yeah. I see how you guys got the 1.
I think we should put just one.
Yeah, I think you're right, Annie.
Without 000?
Yeah, without 000.
That might just be a standard thing that appears in all the tests, maybe. I don't know. I'm just gonna leave it as a 1.
Yeah.
Okay.
I can submit mine with 3 if you want, and then we'll we can see if it works.
Hopefully. Okay, on 10.
So yeah, this is regardless of the distribution of the population. If it's a large sample size, it comes out normal.
Yeah.
The shape's normal because it's a large sample.
Yep.
Okay.
Is that the central limit theorem on number 11?
I think so. That's what I was.
Yes.
Yes, it is.
Okay. So the law of large numbers is what is that exactly? Like, explain the difference between these two, because I think they're
So
so similar.
They're really similar. The central limit theorem is if the sample size increases, just the distribution's normal,
Uh-huh.
and if the law of large numbers, if the sample size is large, then the mean
And multiplication.
of your sample size grows closer to the population mean.
All right. So central limit theorem is kind of just focusing on like what the shape of it's gonna be.
Yeah.
I think so. That's what I understand it as.
Yeah.
Um,
The law of large numbers kind of like as you go along adding more samples, it means that the actual mean is going to get closer to the true mean of the whole population, but you have to, it just goes in like, sets, I guess.
yeah. So I just submitted it before anybody submits it. I don't know if it really matters. 9, I put 3 zeros after it. Maybe it will.
I just submitted it and I got 100%.
And you put 1.
Yeah, I just put 1.
Okay. It accepts both. Great.
Perfect.
Okay. Cool. Oh, so Annie, we were planning on meeting. When were we planning? Wednesday.
Tomorrow at 5:30.
Tomorrow at 5:30. Can we? Okay, that sounds great. If I'm not there, I'll be there at least by 5:45.
Yes, that's fine.
I'm gonna be running home real quick from this meeting, so. Okay.
Does that work for you, Annie?
Sean, would it be easier for you if we went at 6, so you'd have more time?
Maybe. I think we'll get out at 5, and I just know it's gonna take me like 40 minutes to